In our last class, we have covered up to this point, basically. So we need to continue from here. The first thing that we are going to, what was the last idea that we proved in our last class? It was actually the proof of uh, the Pell-Bromogupta equation, right? Oh no, it was the idea that if one of the ordered pairs is if we can manage to find one solution of this equation, we can find infinitely many using this idea that all of the x and y has to be solution. Now, there is a problem related to the Pell-Bromogupta equation that we are going to start our class with. It looks pretty informal, but this is actually a very nice problem. The problem asks that, can you find infinitely many triples of consecutive integers, each of which is a sum of two squares? So in algebra, they are asking if there is it possible for n-1 n and n plus 1 three consecutive integers where all of them are sum of two squares. Is it possible? The answer is it is possible, and it's easy to prove due to Pell-Bromogupta equation. Let's see how. What they're doing is they're considering n to be a square, for example, x square. Then n is clearly a sum of two squares, just x square plus 0 square. And of course, then n plus 1 is also easily a sum of two squares, just x square plus 1 square. All that remains is to prove that x square minus 1, which is n minus 1, of course, is a sum of two squares. They are somehow intuitively, maybe this is a hunch for us, they are intuitively considering that maybe x square minus 1 is going to be a sum of two same squares or equal squares. So they are formulating this equation x square minus 1 is 2y square. And rearranging it, we get an equation like this, which is exactly a Pell-Bromogupta equation. So this has infinitely many solutions, actually, to be honest, and hence it's already proved that we can manage to find three consecutive cases where all of the three numbers are actually sum of two squares. Okay, now we have a proposition here for some integer m and another integer d. If this general Pell-Bromogupta equation has one solution, it has infinitely many solutions. If this idea is true, then all you have to do is manage one solution of the equation. You will get infinitely many. And the proof is pretty simple. Say, for example, x1, y1 is a particular solution that you found. Then x1, y1 satisfies this equation, and they just factorize this equation using the formula for a square minus b square. Now, say, for example, Sn, Tn be other solutions. Basically, we are going to prove that Sn, Tn are all. This is also a solution for every n, and let's see how. If this is a solution of the equation, these two should be in the power, not subscript. Anyway, if Sn, Tn satisfies this equation, then just like this factorization, Sn, Tn would give us this factorization, this equal to 1. Okay, here is a catch. SNTN is not really, let me use another color. SNTN, they are considering SNTN to be solution of not this equation, but the equation where the right hand side is 1. Here, the right hand side is not. So, this equation had, say, for example, a solution x1, y1, and consider n equals to 1, you get a new solution, and for new equation, and for that new special case equation, they are considering SNTN to be solutions, and we have seen that this particular n equals to 1 case has infinitely many solutions, which was exactly the last proposition we proved. So basically, they factorize the left hand side just like before. Then their claim is, if you form this guy xn plus root dn like this, just use n equals to 5 here, you would get x5 and y5 here, and so on. Now take the conjugate of this guy xn minus root dn. Then we would have minus here, we would have minus here. If you take the product of the two conjugate guys, xn plus root dyn and its conjugate xn minus root dyn, then you will have just product of conjugate of this guy and this guy with themselves. So this guy multiplied by its conjugate will produce 1 because this part. Let's use another. Because of the red circle, this guy multiplied with its conjugate will produce n, not 1. And this guy multiplied with its conjugate will produce 1. The overall product will be n into 1. So and on the left hand side, this is just xn square minus dyn square. So we are getting this equals to exactly n, which is the given solution. So for every n, xn, yn, xn comma yn, the ordered pair, xn comma yn is a solution. So since Sn comma Tn are infinitely many, we would get infinitely many Xn comma Dn as well, which proves that this equation will have infinitely many solutions if you can manage to find one solution. And you should be aware that there are possibilities where this equation has no solution. So if you manage one, you will get infinitely many, but you may not manage one at all under circumstances. Okay. Please let me know if you have any confusion anywhere so far. There is another problem next where you are asked to prove that n square plus n plus 1 whole square is a perfect square for infinitely many n. In other words, they are claiming that there are infinitely many perfect squares which can be expressed as sum of two consecutive squares. The proof again is pretty simple. Just expand the n plus 1 whole square to get this guy. Simplify them to get this. And if this is indeed equal to sum m square, then multiply on both sides by 2. This would give us the freedom to express this guy in terms of a complete square again, but not like this one, but in a different way. So 4n square plus 4n plus 1 is 2n plus 1 whole square. We are just left with another extra 1 here. Now we have ended up with an equation like this. Say for example 2n plus 1 is L. So replace this equation to get L square plus 1 equals to 2m square. And you can see that this is just L square minus 2m square equals to minus 1. So if you manage to find one solution of this equation, here capital N is equals to minus 1, right? So if you somehow manage to find one solution for this equation, you will get infinitely many. And definitely L equals to 1 and M equals to 1 is a solution. So there are infinitely many solutions of this equation, which proves the claim. Next comes the 4 square theorem. We already have proved the 2 square theorem. 2 square theorem states that every non-negative integer is a sum of 2 squares. Here in 4 square theorem, just replace that 2 by 4. So every non-negative integer is a sum of 4 integer squares. This is what we need to prove. Now recall that if you remember, you shouldn't you? Oh no, it wasn't a part of quiz 3 syllabus. Anyway, but if you attended the class, you should remember that we use the fact that if you multiply sum of 2 squares, you get another sum of 2 squares. And this can be proved algebraically, but I showed a method where we use this. I used this square times, if you can remember. One student also raised hand and asked how come we got to complex number all of a sudden, if you can remember. So AC minus BD plus AD plus BCI. So this is what we proved. In other words, we took two complex number, Z1 and Z2. We use the fact that modulus of Z1, Z2 is actually modulus of Z1 into modulus of Z2. This is the fact we used to get to a simpler proof of this equation. And this equation helps us because since any two sum of two squares are multiplied, when multiplied produces another sum of two squares, this just means all you have to do to is check if one and the only even prime number two, if these two guys are sum of two squares. They are actually. One is 0 square plus 1 square, two is 1 square plus 1 square. This is a repetition. I already went through this during one of our classes. So then any number you take, any non-negative integer you take is actually a product of primes, right? And each of those primes, if you can prove that any prime can be expressible as a square plus b square, if somehow you manage to prove this, then any integer you take, whatever integer n you take, this is just sum of a product of a few primes. Now, since each of these primes, as we proved, can be expressed as a sum of two squares, their product is going to be a sum of two squares as well, according to this fact. So this equation is really powerful. It was a major stepping stone for that proof. Basically, in case of the four squares, we are going to use the same idea, but now complex number is not going to be helpful. We need to prove that basically, we need to prove that if you, if you want to use the same idea, then we need to prove that if you take two guys who are sum of four squares, one is this one and one is this one, and somehow manage that this is also a sum of four squares. They say this is actually equal to this guy square plus three other similar huge terms square. So if you can manage to prove that taking product of two sum of four squares will produce another sum of four squares, then using the same idea we can prove the theorem. All we have to do is see or verify if one is a sum of four squares, which is true, two is a sum of four squares, which is also true, and for any prime p is a sum of four squares. If we can manage to prove this, then this powerful equation will help us to complete the proof. But how can we prove this? Proving this algebraically is pretty difficult, but again, actually complex number helps us. More specifically, the generalization of complex numbers that we generally teach in the complex analysis course, the quaternions. Those who do complex analysis are familiar with quaternions. Those who are not, for them, here is a brief description. Quaternions are, if you stop here, you get a complex number. If you go further and add two more terms, just like bi, they are just cj and dk, then this is called a quaternion. If you take every possible real linear combination of 1 I, basically complex number is every linear combination of 1 and I, right? Complex number is in a way spanned by 1 and I. Every real linear combination of 1 and I. This guy is every real linear combination of 1, I, j, and k. That's all.
J and k are both root over -1.
I'm going there. I'm going there. Don't worry. Actually, I'm having some trouble with my graphics pen again. Give me a moment, please. Okay. Yes, as he said, I is root over hopefully it's okay now. No, it's not. Okay. Let's try to continue as well as we can. Basically, as he said, for the complex numbers, I square is definitely -1. And for this case, j square and k square is -1 as well. You may wonder, okay, so we know what j square and k square are, their root over -1s, and we know what a root over -1 is. Not really. Basically, we are in a four-dimensional number system. where J and K are J and K are not really I. J and K are two new guys whose square happens to be -1 as well, and we don't know who J and K are. They are not complex I. J and K are not exactly imaginary I. They are new guys in new dimensions, the third dimension and the fourth dimension, whose squares happens to be 1 as well. If they are just root over -1, I mean the traditional root over -1, then there would be no distinguish between J, K or I, right? But that's not the case. Okay, somehow if you multiply IJ, JK and KI, you get KI and J. It almost works like the I cap, J cap, K cap of vector regular 3D vector cases. And similarly, Ji is minus K instead of K. And basically, if you accept this group structure, basically they form a group. 1I, minus I, minus J, minus K, -1. These 8 guys actually forms a group. The group is called the quaternion group. If you accept the group structure, then, and if you somehow define a norm where we know that norm of a complex number is just Z times Z bar, right? So we are going to use a similar definition here, but for the number A plus BI, its conjugate was A minus BI. What is the conjugate of this guy? Just replace IJK by minus I minus J minus K. So Z bar is this guy. So their norm is defined. You can just multiply Z and Z bar. You will see that it produces, using these relations, it will produce A square plus B square plus C square plus D square. Now, in a similar method we use for complex numbers, you can you can prove that if you take 2 sum of 4 squares and multiply them, and use the fact that norm of Z times W is just norm of Z times norm of W, you will end up getting a huge expression which is also a sum of 4 squares. Now the rest of the proof is exactly same as the 2 square theorem. In 2 square theorem, we prove something like this. There is a positive integer m less than p such that mp is the sum of 4 squares. We used 2 squares there. Now it's 4 square here. And you should be able to remember that we have repeatedly reused the fact that m is the minimal case. And repeatedly contradicting the minimality of m about 3 or 4 times throughout the same theorem, we ended up with the conclusion. Exactly same steps are followed here. That is why I'm not going through the same structure again. You can just go through the proof and you should be able to understand. In case if any of you don't understand any part, you can contact me, that's all right. But you shouldn't have any problem since you did not have any problem understanding the 2 square cases. Okay. Then comes Pythagorean triples formation. Basically, okay. I'm trying to use my mouse as much as I can since my pen is giving some trouble. Okay. For example, the Pythagorean equation is a Diophantine equation in a way. That is, you know that 3 square plus 4 square is 5 square. You may be interested in finding other integer solutions of the same equation. You are familiar with some other solutions as well. For example, 6 square plus 4 square plus, I'm sorry, 6 square plus 8 square is 10 square. Now you can see once you have one solution, 3 square plus 4 square is 5 square. Just multiply by some square number a square on both sides. You get 3a square plus 4a square equals to 5a square, which is a bigger solution. Now, if you use a equals to 2, you get 6, 8, and 10. If you use a equals to 3, you get 9, 12, and 15, right? So once you have a particular solution, you can just multiply the equation by any square number. You are going to get infinitely many solutions from that one particular solution alone. Then you can start with 5, 12, and 13, and you will get infinitely many solutions from this guy as well. So all basically what I'm trying to reflect is you can just look for the solutions which are co-prime to each other. That is, you can just look for the particular triplets where x, y, and z are co-prime. That is the minimal case, just like 3, 4, 3, 4, 5, or 5, 12, 13. All the other cases can be reduced to that case. So first of all, the first step while solving a Diophantine equation like this, or while finding the integer solutions of equations like this, the first step we do is consider only primitive solutions. Primitive solutions mean where the solutions are co-prime. And you can see if XYZ has GCD 1, then these three numbers are pairwise co-prime as well. That is, individually XY, YZ, and XZ will have GCD 1 as well. Why? Because say, for example, one of the pairs are not co-prime. For example, if the GCD of this guy is A, then A divides both X and Y. And you can see from the equation that A squared then divides the left-hand side. So A square should divide Z square as well, which means A divides Z, which is a contradiction. So yes, the three guys having GCD1 automatically means the guys are actually pairwise co-prime. Now, all we have to do is look for solutions that are pairwise co-prime. We can further reduce our scope by considering that both x and y cannot be even. If both x and y are even, then z is also even. Then we can just divide by. This violates the fact that the solution is primitive, because 4 is a divisor of both all the guys then. So can x, y, z not all can be even as well. So who's who? First of all, x and y both cannot be odd as well. Why both cannot be odd? Because we know that odd squares are 1 mod 4. We have proved that. So x square is, if x and y are both odd, then x square and y square are both 1 mod 4, producing z square is 2 mod 4. And no number on earth has 2 mod 4 when it is squared. No square is 2 mod 4. Either even or odd doesn't matter. So this is a contradiction as well. So finally, we are reduced to the case that x and y, one of these two guys, x and y, has to be odd, the other must be even, which would mean that z is always odd. Okay. For the primitive solutions, you can see that 3, 4, 5, 5, 12, 13. You can see that z is always odd, and one of x and y are odd, the other one is even. Now, without loss of generality, we are just considering x to be the one that is odd and y to be the one that is even. And let's proceed with that. So what we get is, make y squared the subject. Z square minus x square is simply formula a square minus b square. Now, z is odd, y is odd, so z minus x and z plus x are both odd. Not really, both even. Odd plus odd is even, odd minus odd is even. That is why I can just divide both of them by 2 and I will still get integer products, right? But dividing both of them by 2 means dividing by 4 on both sides. So here we have y square by 4, and here we have what we already asked for. Now see, my claim is these two guys are co-prime. Why? Because, say for example, if they have a common divisor a, then a divides this guy, a divides this guy, so a should divide their sum and their difference. What is their sum? X gets cancelled, we have 2z by 2, which is z. So their sum is just z. And a cannot divide z. Why? Because what is the difference? You can see their differ, just like their sum is z, their difference is x, because z gets cancelled out. So their difference is x, and a divides their sum, that means a divides z, a divides the difference, that means a divides x, which contradicts the fact that x and z were co-prime. We have a common divisor a for x and z. This is a contradiction. So my claim is true. These two guys cannot have any common divisor. So they are co-prime. Now, on the left-hand side, we have a square here. A square number is expressed as a product of two co-primes. Two co-prime means none of the prime factors of this guy is going to be present as a factor of this guy, and none of the prime factors of this guy is going to be present as a factor of this guy. So there will be no repetition of prime factors, which means if the product has to be a square, individually both of them has to be square. It's not possible that this guy will produce 3, this guy will produce 3, overall their product 9 is a square. This is not going to happen because they do not share any common prime factor. So since the left hand side is a square and the right hand side is a product of two co-primes, individually both co-primes has to be square. So let us consider z plus x by 2 equals to r square, z minus x by 2 is s square, and definitely r is the bigger one, s is the smaller one because we have subtraction here and addition here. Now, R and A, don't forget that R and S has to be, both R square and A square are co-prime, they are co-prime, so R and S has to be co-prime as well. Now, make Z and X our subjects and solve for them to get Z is just R square plus A square, X is R square minus A square. Put these values here to find Y in terms of RS as well. You will get that Y is 2RS. So XYZ looks like this, and what this means is as long as you randomly pick two co-prime numbers RS where only condition is R is greater than R is greater than R is greater than S and S is greater than 0. This is the only condition other than co-prime. Then any pair of values RS you choose under this condition, put them here, you will get a triplet which satisfies the Pythagorean equation. So using, technically this is a solution actually. Every solution of the integer solution of the Pythagorean equation lies here somehow. You actually successfully found every solution of the Pythagorean equation in terms of two parameters R and S. Now, this was a pretty nice solution or nice technique to get the solution, but let us solve the same equation or to find the same solution using a different method. Why we are using a different method is, even though we already got the solution, because this second method is more general. If you have any conic, you know what a conic is, right? A conic is a second degree equation, right? And geometrically it is just, if you take a cone, for example, this is 0, 0, 0, so this is equation of a cone. If you take any cross section, for example, if you take a cross section like this, you would get a parabola in the cross section. If you get a cross section like this, you would get a circle. Circle is a special case of conic, right? Circle is actually a special case of ellipse. But if the it is a, basically the, I made a mistake, the conic actually goes on. So when you take an intersection like this, you would get an ellipse as an intersection. But what about hyperbola? You can, most of you already know this, I think. If you take a cross section directly vertical, you will get hyperbola, and similarly you can produce parabolas as well, etc., etc. So second degree equations are called conic because they are sections of conic, sections of cone actually. Anyway, if you have any somehow, let's see how this is related to the solution of the Pythagorean equation. If you have, we are trying to find the integer solution of this equation, right? Now divide by z square on both sides. They should put square here and here. So what we have is x by z square plus y by z square equals to 1. Now consider x by z to be alpha and y by z to be beta. Now you should be able to see that alpha and beta are no longer integers, right? Alpha and beta are rational numbers. So we are now interested in solving this equation for rational integers. alpha comma beta, rational pairs alpha comma beta. Now, this is the equation of a circle x square plus y. This is the equation of the unit circle. So technically, we are just trying to find all the rational points on a unit circle. And circle is a special case of ellipse. Ellipse is a special case of conic. So circle is a special case of conic, or in other words, circle is a special case of 2-degree equation. If you have not just a circle, but any 2-degree equation, you can follow the procedure that we are going to follow in a minute. So we have a circle, and for the method to work, you need to find at least one rational solution for this equation intuitively. And this is easy because 1, 0 is a solution, no doubt. 1, 0 is a solution, is a point on the circle. This particular solution is an integer solution, but this is a rational solution as well. And we are now particularly interested in rational solution. Now, if you manage to find one rational solution, say for example, there is another rational solution uv, another rational point uv on the circle somewhere. Say this is a circle, you get 1, 0 here. Maybe this is u comma v. Now find the equation of this line. Equation of this line is y equals to m into x minus 1, where m is the slope, v minus 0 divided by u minus 1. So this is the slope of the equation. Now, as you can see, if uv is rational, 1, 0 is also rational, then the slope is going to be simply y2 minus y1 divided by x2 minus x1. So if this is x1 y1, your first solution, and this is x2 y2, your guessed solution, the second solution, which we are yet to find. If both of them are rational in coordinates, then m is always going to be rational. All right. So we are going to use this fact that m is always going to be rational. How? What we are doing is substituting. We know the value of m here, and if uv is a point on the straight line, uv is a point on both the straight line and the circle from our last page, right? So uv satisfies the equation of this circle and satisfies the equation of the unit circle as well. This straight line and this, sorry, let me rephrase. uv satisfies this straight line's equation as well as the equation of the unit circle. So what we are going to do is solve these two equations. So we have two equations. V is equal to m into u minus 1, and you have u square plus v square equals to 1. You are going to solve this equation. So put the expression of v here, plug the expression of v here. After plugging, you will get an equation in terms of u and m. Make u the subject. At the end, you will get a solution u in terms of m. Putting this value of u again in the straight lines equation, you will get to find the value of v. So finally, you get u and v. Using this, as you can see, this is going to, this is basically a point on the unit circle. If you take the square and add them, you will get 1. You can check that. And definitely it has to be true because we use this equation. Anyway, these coordinates are going to be rational as long as m is going to be rational. So all you have to do is put different values, rational values of m, to get different coordinate points on the unit circle. And this method, the same technique, can be applied to any quadratic equation, any 2-degree equation, for example, parabola, or if the initial geometric structure was not the unit circle but the parabola y square equals to 4x, or an ellipse x square plus 2y square is 1, etc., you'd still be able to apply the same technique. Just find one particular rational solution somehow, consider another rational solution uv, take their slope or take the straight lines joining them, substitute v in the equation of the given conic, make u the subject, then using that value of u, solve for v as well, you get uv just like this. And these are all the solutions of the circle. But do not forget that we were not actually interested in the unit circle. Our original interest was not rational solutions but integer solutions, and not on the circle but on this particular surface, basically the Pythagoras equation. So that that is yet to be determined, and we are not far from the final solution, because if you just put m equals to I don't know why they used, okay, they used minus sign here because we have minus here. They could use just m equals to r by s, but in that case, they were going to produce negative integer solutions. But we are particularly interested in positive integer solutions. That is why instead of m is a rational number, it could be r by s, but instead of putting r by s, they are putting minus r by s to get positive solutions. So put minus r by s and simplify, you will get uv equals to this guy. So if uv equals to this guy, so can you see if uv is this guy, what was u? U is x by z and v is y by z, where x, y, z are integers, but x by z, y by z are not. They are uv, they are rational. So all you have to do is consider this to be x, this to be y, and these common two denominators to be z. Then you would get this pair, the same pair we got algebraically. So this method is, they are calling this method the slope method throughout the lecture. Not we are going to call this method the slope method as well. We will see that this same method can be used to find the solution of many Diophantine equations. Please let me know if you have any confusion so far. And if the meeting, I think we have 2 minutes left. I think I'm going to close the meeting. Please rejoin, because otherwise the meeting would abruptly stop in the middle of the proof. Okay, let's continue from where we left. The next thing that we are going, okay, there is one thing, I have already mentioned that actually. It's possible that the equation you are trying, the Diophantine equation you are trying to solve does not actually have any solution. So it's, the slope method requires you to basically start with a solution already. You have to solve intuitively or in other ways. You have to find one solution at least at the beginning. But it's possible that there are no solutions. For example, they are giving an example. If you have a quadratic equation x squared plus y squared plus 1 equals to 0, you cannot find any rational points on this curve, because sum of two squares is never going to be negative. So you don't have any starting point, and hence you cannot start the process. So you cannot have the infinitely many solutions because there are not a single solution of this equation. So it's possible. Anyway, another famous equation that does not have any solution is x to the power n plus y to the power n equals to z to the power n for n greater or equal to 3. Here x, y, z and all are integers, and we are particularly interested in positive integers. So x, y, z and all are positive integers here. You know that Fermat's last theorem states that this particular equation has solutions only for up to n equals to 2. After that, you cannot find any solution. In this lecture, we are particularly interested in solving the case for n equals to 4. So we are going to show that x to the power 4 plus y to the power 4 equals to z to the power 4 has no integer solutions. But in the theorem, they are proving that x to the power 4 plus y to the power 4 plus z square, not 4, z square, this equation has no solutions. But proving this automatically proves this as well. Can anyone tell me how or why? Okay, you should be able to see that basically, yes, please continue.
No, I misunderstood.
Okay, so the idea is any square, any z to the power 4 is also a square, but any square is not a power 4. So if you can prove that this equation has no solutions, you have already proved this statement and many other statements
Right.
along with it as well. So this is a stronger result, right?
Yes.
Okay, so yes, so we are going to use the stronger result, and for that we are going to use a technique that famously known as Farmer's infinite descent. You can see the name written here, Farmer's infinite descent. This method actually uses this idea that if you somehow you manage to develop a process that lets you find a smaller solution once you have at least a particular solution. For example, if you have a solution xy, then you are guaranteed to manage another solution rs which is somehow smaller than xy. Then this would mean that you can just repeatedly go down as less as you can and find many solutions, but you have just finitely many. Since you are not ascending, you are descending, so there are just finitely many possible solutions downward, and this fact would lead to a contradiction. So basically what we do in this method is somehow in terms of at least one of the parameters we declare the minimum solution, and then we manage to produce a further smaller solution which will contradict the minimality. In this case, we are defining that size by value of z, which means if you have a solution 1, 2, say for example 1, 2, 3, and another solution 1, 1, 2, another solution 2, 1, 2, for example, even though x is greater in the number in the triplet I wrote below, but this is smaller because z is smaller for this triplet. I think you got the idea. For two particular triplets x, y, z and rst, we will claim that x, y, z is smaller if z is smaller than t. We are not interested in comparison of x, r and y, s. We are just interested in z. If z is smaller, that particular triplet is called smaller. If this is how we define the size of a solution, or if this is how we establish the comparison of two solutions, then there is, since we are dealing with only positive solutions, there has to be a minimum solution, that is minimum in terms of z. Let us consider that solution. Now, we are definite that x and y are co-prime, because if x and y are not co-prime, they have a common divisor a, which would mean that a to the power 4 divides the left hand side. So a to the power 4 divides the right hand side as well. So a to the power 4 dividing z square means actually a square dividing z, which would mean we get something like this. And this would mean we got to a smaller result because z is greater than z by a square, which is a contradiction. So first of all, we have to consider that x and y are co-prime. Now, x to the power 4 can be written as x square whole square, same for y to the power 4. So we have a situation that looks exactly like a Pythagoras equation. And we already just solved Pythagoras equation. Using that experience, we can say that, or safely claim that, all the solution triplets are like this, as we have solved r square minus a square, 2rs, and r square plus a square. Only condition is r greater than s greater than 0, and r and s are co-prime. Also, r and s are opposite parity. That was a given. That was a given, of course. So now, as you can see, x square is r square minus a square, which means we have another equation here which also looks like Pythagoras equation. X square plus a square is r square. And this equation can be solved in the exact manner as well. And of course, you have x square is already odd from the initial consideration. In our consideration without loss of generality, we considered that this guy is odd, this guy is even, this guy is odd. So x is odd, that means x square is odd, no doubt. And for similar logic, if both of them are odd, then both of them are 1 mod 4. So 1 plus 1 is 2 mod 4. The right hand side is a square. Any square can never be 2 mod 4. So again, we have s is odd. So x is odd, s is odd. Sorry, s is even, s cannot be odd. So x is odd, s is even, r is odd. And just like before, this is again a Pythagoras equation and it has solution of this form. Again, these are the conditions. Opposite parity is already a given. Now, we are going to repeatedly use the same idea. Please stay with me. Now, y square is 2rs. So, and s is even, right? So, if I divide by 4 on both sides, I get r times s by 2 on the right hand side. And since s is even, s by 2 is an integer. So this product is an integer, so y is even as well. So y by 2 is an integer as well. And we are going to use a similar argument as we already used. This guy is a square. And since r and s are co-prime, r and s by 2 are co-prime as well. So right hand side is a product of two co-primes. Left hand side is a square. So individually, both of these co-prime guys must be square. So let's consider that s by 2 is m square and r is n square. Now, s by 2, as you can see, s is 2tu. So what is s by 2? T times u. And t times u is exactly equal to m square. With t and u co-prime again. So two co-prime products producing a square. So each of them must be square again. So t is a square, say k square. U is a square, say l square. Now what we have, r is, basically what is r? R is, here you can see r is t square plus u square. And from another case, r is n square. So t square plus u square is n square. We get t square plus u square is n square. Now t is k square, u is l square. Put k square and l square in here to get n square equals to k to the power 4 plus l to the power 4. What we managed to do is actually get smaller result. You can see that k comma l comma n is a solution to the original equation. Just observing the structure, this is a solution to the equation x to the power 4 plus y to the power 4 is equals to z square. So this is a solution to this equation, and this is a smaller solution than the original solution x, y, z. Why? Because n definitely less or equals to n square. This is true for every integer. Equality holds for n equals to 1 only. For any integers greater than 1, any integer greater than 1, n is always going to be strictly lesser than n square. N square is r. R is less than r square. R square is less than r square plus a square because you are adding something. And r square plus z square is z, as we have seen earlier. So n is less than z. So this solution is a smaller solution, which contradicts the fact that our original solution xyz was the smallest. This means that this particular equation cannot have any positive integer solution. And this would definitely imply that Fermat's theorem is proved for n equals to 4. We have already provided the logic. For example, in the exam, if I ask you to prove Fermat's last theorem for n equals to 4, first of all, you have to write 2 or 3 lines explaining why proving this theorem is sufficient to prove the Fermat's theorem for n equals to 4. The argument I have used orally, right? 2 or 3 lines, write 2 or 3 lines defining or defending your argument that proving this theorem is enough. Then provide the proof of this theorem, right? I think you got the idea. Please let me know if you have any confusion anywhere. Now we have a few examples, very nice examples. When you have to prove that a particular any particular Diophantine equation does not have any solution, then one way is to use modular arithmetic. The idea is, if this equation does not have any solution for example, this equation, if you can prove that this equation does not have any solution mod 4 or mod 5 or mod 10 in any particular mod n, then it cannot have any solution in general. Because taking mod gives you extra facility to, there are equations that do not have any solution in general, but taking mod gives you solution, right? For example, x square plus 1. equals to 0. This equation does not have any solution, right? But if you take mod 3, then it does have solution. How? In the world of mod 3, if you, I mean, does it though? Give me a moment, please. Uh, okay, let's give even a simpler example. Say the equation was x squared plus 3 equals to 0. This equation does not have any real solution at all, let alone positive integer solution. But if you take mod 3, you can see that this equation does have solution. X equals to any 3k is any x equals to 3k will satisfy the equation mod 3. So there are cases where the equation does not have any solution in general, but they have solution modulo some number. But vice versa is never going to be true, because mod gives you extra facility. It relaxes the condition. So even after taking mod, this does not have any solution, then or generally the general equation would not have solution at all. So let's use the fact. Take mod 4 on both hand sides. So you can see that 4y cube gets vanished because we are taking mod 4. So the equation becomes x squared is 3 mod 4. And we know that no square integer is 3 mod 4. Odds are 1 mod 4, even are 0 mod 4. Any number square is either 0 or 1 mod 4. So there is no number whose square is 3 mod 4. So this equation does not have any solution. So the original equation cannot have solution either. Similarly, if you are given a bit of more complicated equation like this does not have any solution. Why? Because if you take mod 7, for example, you can understand that if when you apply techniques like this, generally you look for coefficients here as the modular as a choice of the modulo world, right? We are taking the modular 7 here because we have 7 here. This gives you the facility that 7z cube gets cancelled. You are left with just x cube plus y cube equals to 3, but in mod 7. Now this equation does not have any solution because you can see that 7 is a prime number. So let's use Fermat's little theorem. So phi of 7 is 6. Any prime number p has phi value p minus 1. So this is phi of 7. So x to the power phi of 7 is 1 mod 7. So x to the power 6 is always 1 mod 7, whatever the value of x is. That means x cube square is 1 mod 7, which means x cube is just plus minus 1 mod 7. The only case, exception case is x equals to 0. So basically, cube of a number takes 3 possible values modulo 7. They are 0, 1, and minus 1, right? So x cube is either 0, 1, or minus 1. Y cube is also either 0, 1, or minus 1. You can take any of those combinations, you are never going to get 3. So this equation is not valid for any integer xy. That means the original equation cannot have integer solution as well. Okay, now we have another equation, and we're going to use to prove. They're claiming that the only solution to this equation is 0, 0, 0. So this equation does have solution, that's for sure. But they are claiming that this is the only solution. There is no positive integer solution. There is non-negative integer solution, the trivial one, but there is no positive integer solution. How can we do that? How can we prove that? We are going to use Fermat's descent method. Let's choose the smallest possible non-trivial solution xyz, and the smallest case must be primitive, right? So otherwise we can just divide by the common divisor to get smaller solutions. So basically the GCD of xyz is 1. Now let's take mod 2 in the original equation. If you take mod 2 in the original equation, you can see that these two terms are vanished. You are left with x cube equals to 0. And x in mod 2, of course. And x that means x is 0 mod 2. If x cube is 0 mod 2, x is 0 mod 2. So write x equals to twice of some integer. Since this is 0 mod 2, it's even, right? So substitute this guy in the original equation. In case of x cube, you get now 8x dash cube. Divide by 2. Again take mod 2. then you see that x dash and z gets vanished. We are all that's left is y cube. So y cube equals to 0 mod 2 again gives you y is a multiple of 2. So y is 2y prime. Putting that and again dividing by 2 on both sides, you will eventually get z is even as well. This means that 2 divides x, y, z. So x dash, y dash, z dash is actually x, y, z divided by 2. So this leads to a smaller solution which contradicts the minimality of the starting solution. We are exactly using the Fermat's descent method, right? So infinite descent method. So according to that method, we are led to a contradiction. So there cannot be any solution other than 0, 0, 0. We this structure in the world of in the world where people are, I mean, obsessed with finding rational solutions of curves, rational points on curves, this particular structure of this family of curves is very, very, important actually. This belong to the family of elliptic curves. That's not, elliptic curve is not really related to ellipse. Elliptic curve is not a part of this course, but I'm just mentioning because we got involved with this somehow. So consider a special case where capital D is 7. So the claim is this equation has no integer solution. How do we prove that? This is basically they're mentioning it as a theorem, but this is an interesting problem as well. And I can just use other numbers than 7 as well, right? How do we prove that? The proof is not very difficult actually. First of all, we are interested in positive integer solutions. Okay, interested in integer solutions. Okay, that means 0 is acceptable. So y square is never going to be negative, that's for sure. Whatever the value of y is, so y square is greater or equal to 0. That means x cube plus 7 is greater or equal to 0. So x cube is greater or equal to minus 7. What is the immediate next bigger number that is a cube from starting from minus 7? You can see that this is just minus 1. Between minus 1 and minus 7, there is no integer which is a cube. So, and since we actually left from minus 7, we cannot use equal sign again. So x actually is greater than minus 1. I think there shouldn't be any equal sign here. Okay. This gives us the situation that the right hand side is never going to be 0, because if you put minus 1 here, you already get something that is 6, right? If you put the next bigger integer 0, you get 7. If you put bigger positive integers, you get bigger numbers, larger numbers. So there is no chance that the right hand side is going to be 0, right? So we are definitely sure that if this equation does have a non-negative solution, it is going to be positive solution. We are not going to get 0. Now, say for example, if x is even. If x is even, then even number cubed is 0 mod 4, right? So 0 plus 7 is 7 mod 4, and this is congruent to 3 mod 4. So if x is even, we get that y square is 3 mod 4, and we already used this many times. In no square can be 3 mod 4. So x cannot be even, x has to be odd. If x is odd, then what is x cubed plus 7? Odd plus odd is even. So x cubed plus 7 is exactly equals to y square. That means y square is even, which means y is even. If y square is even, then y square plus 1 is odd. Out of nowhere, I am suddenly interested in y square plus 1. So on the right hand side, I get x cubed plus 8. It's not out of nowhere, basically. It's not pulled from the blue, because you can factorize x cubed plus 8, and factorization almost always helps, right? So this is just x plus 2 times this guy. Now, here is an interesting argument. Y square is even, y square plus 1 is odd. Now, if there is a prime p that divides y square plus 1, since y square plus 1 is odd, that prime cannot be 2, that must be any odd prime. So p has to be odd prime. And y square is, if you take module, that means y square, if p divides y square plus 1, then y square plus 1 is 0 mod p, which means y square is minus 1 mod p. And now we have proved this in our mid exam as a problem, right? We have seen that if in under any situation this is true only if either p is 2 or p is 1 mod 4, but p is not 2 because y square plus 1 is odd and p is a divisor, so p cannot be even. The only possible situation is p is 1 mod 4. So we have proved that through argument that if any prime divides this left hand side, that prime has to be 1 mod 4. Any prime that is of the structure 3 mod 4 cannot divide the left hand side. Now, whatever the right hand side, x cube, basically if you take mod 4 on the right hand side, then 8 gets vanished, right? Uh, Observe from here. Take basically we have seen that y is even, right? So basically x cube equals to y square minus 7. So if we have seen that y is even, so if you take mod 4, y square gets vanished, you get minus 7. And we are in the world of mod 4, you can just add 8 here, any multiple of 4, we can add 8 here. So this is just congruent to 1 mod 4. So x cube is 1 mod 4. And x cube is 1 mod 4 means x is 1 mod 4. X is 1 mod 4 means x plus 2 is 3 mod 4. So this guy is 3 mod 4. And we have seen that if any number is 3 mod 4, it must have, we have already proved this in one of our earlier lectures, that any number which is 3 mod 4, it must have at least one factor, prime factor, which is 3 mod 4. So there has to be at least one prime that divides the right hand side, which is of the form 3 mod 4, which contradicts the fact that all the prime factors of y square plus 1 are of the structure 1 mod 4. So this leads to a contradiction, which means this solution equation cannot have any integer solution. We are almost there. The next topic is rational points on conics. We have already mentioned that some mathematicians are obsessed with finding rational points on conics and in particular elliptic curves. Say for example, this is a general, basically a conic is any, as I have already mentioned earlier, a conic is a plane curve cut by a polynomial of total degree 2. So let that polynomial be this guy. So any point that actually is rational and on this particular curve is of our concern. Now they are giving an example of this circle, and you can see that 1, 2 is already the point that satisfies the equation of the circle. This point is on the circle. Now they are using the slope method, as we have already used a few minutes ago. Using the slope method, they found all the possible solutions. All right, so this is a repetition of an example. Now while trying to find rational points on curves like this, or let's not talk geometrically, while trying to find rational solutions of Diophantine equations like this, there are some reduction of, we can narrow down our scope. How? Let's see. First of all, I'm not going through the proof because these can be realized intuitively pretty easily. That is why I'm not going to go through the entire proof or proof of every step. But you can see if you replace x by, okay, someone is, all right, that's all right. So one student said that he is having net issues. He will try to reconnect. I'm replying to him. That's all right. Okay. So if you replace x by z and y by z, in the equation, you will get an equation like this. This is pretty simple. Just replace x by z and y by z. Now, finding rational solution on this curve is equivalent to actually finding rational points on this curve or rational solution of this equation is equivalent to finding integer solution of uh, this equation. So this is the first reduction. We scoped our narrowed our scope down to integer solution of another equation, not the original but another equation. They narrowed the scope further and they deduced that, I mean, by completing square, they use some pretty easy algebra to complete the square wherever possible in this particular manner to reduce to a structure of this form. That means all we have to do is try to solve, convert our, if we can develop a method to solve for integer solutions of equation of this form, then we are okay, because any equation that looks like this or the original equation can be reduced to an equation of this form. And finally, we can always narrow down to the case where we need to find the primitive solution, because you can just divide by the GCD, right? So you can just consider that A, B, C are co-prime. So the final idea is, all we have to do is find a method or make sure that solution exists for an equation of this form, which is a pretty simple form where A, B, C are co-prime, which would mean that their product does not have any repeated prime number, which means that ABC is square free. So the theorem is, the result is summarized in Legendre theorem, which says that ABC be non-zero integer such that ABC is square free. Then this particular solution has a non-trivial rational or integer solution if and only if these two conditions are true. Number one, ABC don't all have the same sign. And number two, minus AB is a square mod C, minus BC is a square mod A, and minus AC is a square mod B. Okay, I went through the proof, and the proof is pretty simple. The only place where one might get confused is this place. I want to keep the proof as a homework for everyone, but here some of you might get confused. That is why I'm explaining this step here. At some point, we got this expression to be congruent to. Basically, they proved that this expression can be factorized into linear factors like this for mod A, and they claim that similar can be argued for mod B and mod C. So overall, they claim that this guy can be factored like this for mod A, like this similar structure for mod B and mod C as well, linear factors. Now, the coefficients are different here, but you can always, what you can do, say alpha 1, these are three equations, but we can combine them into one equation mod ABC using Chinese remainder theorem. How? What you can do is, somehow, if you can find a common value alpha, which is congruent to alpha 1 mod A, congruent to alpha 2 mod B, and finally congruent to alpha 3 mod C. If you find one such common alpha, then you can just replace all these three guys by just alpha. Similarly, you can do the same for all these beta 1, beta 2, beta 3, replace them by a single value beta. And finally, gamma 1, gamma 2, gamma 3 by a single value gamma. Same argument for these three as well. Then you can just write the expression in a single equation. This is just this product mod ABC. But how can we manage some common value alpha? This is true because we can just use, this is just a simple case of Chinese remainder theorem. This is our X, this is A1, A2, A3, this is N1, N2, N3. So you can just use Using Chinese geometry theorem, you have to solve 3 system of equations exactly. And so after that, you will be able to, you don't have to solve for the proof of the theorem. For the theorem, all you have to do is claim or argue that we can manage to find a solution. Solving is not necessary for the theorem. So you can manage a solution for this equation. You can manage to write this guy as a product like this mod ABC. And then they used a simple geometrical box to argue that um, to complete the proof. Actually, basically the rest of the proof, as I went through, I can remember that the rest of the proof is pretty straightforward. So I want to leave the proof of the theorem as a homework. Please go through the proof and let me know if you have any confusion anywhere. Then I will of course try to remove the confusion. That will be all. You can uh, uh, I mean, best of luck for the final exam. And most of you have done very well in quiz 3. So I hope your final will be, I mean, you will have a great final exam as well. That's all I have to say. I think so. So that would be all. If you have any queries, you can ask me. Otherwise, I'm leaving the ending the meeting. Okay. Okay. Best of luck, everyone.